Hi, I'm Ritvik, and today I'm going to discuss the solutions of Codeforces Round 1071 Div 3. Okay, let's start. Coming to the A question, we are given two variables k and x. I'll initially summarize this question. And what we have to do is we have to construct a string s such that it only uses the first k lowercase letters of English alphabet, and also for every pair of integers j minus I, such that j minus I is divisible by x, s of I and s of j should be different. Basically the second condition here tells us that if there are two indices having the same modulo, then their characters must be different. uh, so so in order to construct the string of maximum length, uh, let's take the indices. Like for example, let the indices be 1 2 3 4 5 6 7 and k value equal to 3. I'll only focus on modulo 3, index modulo 3 equal to 1. So I'll focus on only these vertices 1, 4, 7, etc. And in order to maximize the string length, what I have to do is I have k distinct characters, right? So at every such modulo, I'll put all k distinct characters. For example, here I'll put k1, k2, k3, so on. So our final answer will be like we will have x different modulos, as we are doing modulo by x, and at every different modulo I am putting k different characters. So maximal length of string I can construct is k into x, as they have asked in the question. Like uh, we have to output the smallest 10 such that no valid string of length n exists. As I can construct the maximal string length of length k into x, the smallest 10 which I can't construct is k into x plus 1. So simply the code for this problem is to output k into x plus 1, and that's all. Okay, coming to the second question. Yeah, we are given an array A of n integers, and what we have to do is we can choose at most one index and remove that element from the array. We have to minimize this sum, like modulo sum of adjacent elements in the final array. Like for example, if I have erased an element k, my resulting array will consist of a1 to ak minus 1. I have excluded the ak, and ak plus 1 to an. Okay. Now what I want is I want to minimize the modulo sum of this new array. Or here we have to focus on point that we can choose up to one index. So also we have to consider the case where we are excluding none of the elements. And that's all. Coming to constraints, we got n equal to 2e5, and array elements lie from 1 to 100. Okay, now coming to the code. Let's assume that this is our given array: a1, a2, a3, a4, a5, consisting of 8 elements. So what we are finding is basically a1 minus a2 plus modulo of a2 minus a3 plus modulo of a3 minus a4 plus modulo of a4 minus a5, so on. Okay. Now suppose initially we can initially store the initial modulo sum in a variable, like the case where we are excluding no element. Suppose we are excluding one element, like in this case, if I choose to exclude a2, then choose to exclude a2, then what will happen from the modulo sum? Here this term will vanish, a2 minus a3, and this term will vanish, and I'll get a new term a1 minus a3. So basically generalizing this case, if for example I am excluding some element ak, excluding some element ak, what will happen is its exact just previous element is ak minus 1 minus ak, and its next element is ak plus 1 minus ak plus 2. Okay, so basically all the sums and so on, the previous and next one. So all the sums before this part will remain as it is. Only terms that will be affected are these two terms, and all the terms after this will remain as it is. So coming to the affected terms, what we'll do is we'll remove these two terms and add simply a new term ak plus 1 minus ak minus 1. Okay, so here, as we know that all the previous and all the next terms are same, we can simply calculate the prefix sum till index k minus 1, and suffix sum till index k plus 1. And suppose if we are removing an element ak, what I am gonna do is my new sum will be prefix sum of modulo sums till k minus 1 plus suffix sums of modulo sums from k plus 1, and the my newly added extra term ak minus 1 minus ak plus 1. So we have generalized the case where we are removing ak, and this whole thing, this new sum can be calculated in O of 1. Okay, so next step is to simply iterate for all case over k equal to 1 to k less than or equal to n. I'll simply calculate the new sum in O of 1, and I'll have a some variable where I'll store the initial modulo sums where we have no exclusion, like in the case where we are including all the elements. Okay, and what we'll do is we will do minimum of the variable equal to minimum of this our variable comma new sum here, and simply we'll output this minimum value, and this minimum value will be our answer. Okay, coming to the code of this question. Initially I have taken input of the array and created prefix and suffix array. Here prefix I equal to absolute of ai minus 1 minus ai minus 2. Like prefix I contains the modulo sums till index I, and suffix I contains, similarly in the way I have calculated prefix, I will calculate suffix in reverse manner, and suffix I contains the modulo sums from L n till I. Like prefix I contains modulo sums from I to 1 to I, and suffix I contains modulo sums from I to n. Okay, and coming to the variable, I have initially prefix n contains all the modulo sums. Like prefix n means we are not excluding any of the elements. Like I am taking the modulo sums of all the elements, a1 minus a2 plus a2 minus a3, so on, without excluding anything, an minus 1 to an. So that is the value of prefix n, no exclusion case. and I have iterated the for loop, and simply I have a variable like if we are adding a index I, this is the new term that's gonna add, and we are gonna add prefix of I minus 1, suffix of I plus 1, and our new term, and the variable will calculate the minimum value of this term over all possible exclusions. Like here for I equal to 1 I am excluding the element at index 1, for I equal to 2 I am excluding the second element, so on, and finally outputting that one, and that's all. Okay, now coming to the third question. We are given an array and what we have to find is an integer x. We have to find the value k such that for all elements in the array, I'll conduct this operation ai equal. I'll take the modulo by x, and that x must be at least k. Okay. And final goal is to make all the elements of the array equal. So what we have to find is among all positive integers k for which we can do, we have to find the maximum k such that we can make all the elements in the array equal. Obviously we can see that for k equal to 1, our array will always be equal. Like if we do modulo of all elements by 1, we'll get the answer as 0, and our condition is satisfied. But that is the minimum value. We have to find the maximum value of k such that all elements will become equal. So here let's assume that we are given an array and initially we'll sort the array. Okay. After sorting the array, let's just focus on the minimum element of the array. Like I'll check the case in which k equal to my minimum element of the array, or k can be greater than my minimum element of the array. Like here, if the value of k is greater than my minimum element, then obviously my minimum element a1 will remain unchanged. So after applying modulo, all elements will become equal to a1, as a1 is greater than k, a1 modulo k equal to 0. A1 modulo k equal to a1. So finally our a1 remains unchanged. So in order to meet our goal, we have to make all the elements equal to a1. Okay. So here our next observation is that if we have another element a2, second element, or any other element which is greater than a1. Okay. If we take a2 modulo k, what we want is a2 modulo k must be equal to a1. So the maximum value of k, like here note that if my k equal to a1, not k, x, then my x can be greater than or equal to k. So maximum value of k such that a2 modulo maximum value of x such that a2 modulo x equal to a1 will be a2 minus a1. When will this case when will this case be satisfied? If let's check the edge case for here. If a2 equal to 2a1, then a2 minus a1 equal to a1. So in this case a2 modulo a1 will be equal to 0, which won't be satisfied. So for all values where a2 is greater than 2a1, we can see that a2 minus a1, a2 modulo a2 minus a1 equal to a1. Okay. So from here what we can conclude is that after sorting the array, if the value of a2 is greater than 2 times a1, then we can simply take our k equal to, our k will be a2 minus a1. Like for all other elements also, for a3, if I take a3 minus a1, a3 modulo a3 minus a1 will be equal to a1. So here the minimum value, the maximum possible value of k will be so and so. Here the x will be greater than or equal to a2 minus a1. As a3 is greater than a2, a2 minus a1 is a3 minus a1 is greater than a2 minus a1. Okay. So we have handled the case where a2 is greater than 2a1. Now coming to the case where a2 is less than or equal to 2a1, what we can do is here for a2 is greater than 2a1, the minimum possible value of k is minimum possible value of k comes in the case where a2 equal to 2a1 plus 1. Here what I am getting is the value of k equal to a1 plus 1. Okay. So coming to a2 less than or equal to 2a1, I'll first see that if my value of k can be equal to a1, because that is the best possible value I have right now. Okay, a1 plus 1 is not possible because the a2 condition has not been satisfied. So I'll check for a1. If I have k equal to a1, then what will happen? I'll simply target to make all the elements 0 in the array. Like for example, for a1 I'll apply a1 modulo a1. I'll make it 0. For a2 I'll apply a2 modulo a2. That's equal to 0. As a2 is greater than or equal to a1, the value of x can be anything greater than or equal to k. So and so for all elements, I'll simply apply modulo with that element itself and I'll make it 0. So in the case where a2 is less than or equal to a1, our k value can be simply equal to our minimum element. In the case where a2 is greater than a1, our k value will be this, and in the case where a2 is less than or equal to a1, our k value will be this. Okay, coming to the code is pretty simple. Here if I'll initially sort the array and check this condition. If second element, if the second element is greater than twice the first element, then I'll simply print the difference, or else I'll print the value of first element itself, and that's all. Coming to the fourth question. We are given an integer n, and we have to consider all the permutations of the array containing elements from 0 to 2 power n minus 1, that is 2 power n elements. And here a function is defined such that s of p equal to summation of popcorns of and of first I elements of the array, like summation of popcorns of all prefix ands of the permutation. Okay. Here the pop count is simply the number of 1 bits in binary representation of a number. For example, pop count of 5 equal to 2, as 5 contains two ones, 1 0 1, and that's all. So next, a permutation is considered sacred if it maximizes the sum S of P. Okay, and among all such permutations, we have to find the lexicographically minimum permutation. And coming to the constraints, we are given 16 test cases, and the value of n is the n is bounded by 16. As the value of 2 power 16 is less than 1e5, we can write a O of n solution in this case. Okay, let's go to the logic. Here, as we are taking the prefix ands of a permutation, the maximum value of prefix and initially will be, suppose we have n equal to 4. We have permutation containing 0 to 2 power 4 minus 1. I am taking 4 as an example. So initially, to maximize the bitwise like the value of first term in the sum, what I'll take is, I'll initially take 2 power 4 minus 1, which has 4 set bits. Okay. So first I'll get my sum pop count as 4. And second, I know that even if I add any integer between 0 to 2 power 4 minus 1, it has at least 1 bit unset. So my second value will be 3. Okay, second value will be 3. So in order to get the smallest integer that makes the second value 3 is this one. Now if I take AND of these two, what will happen is the first bit will become 0 and I have 3 set bits and my pop count is 3 here. Okay. So coming to next step, my pop count, my next nearest pop count is 2. Here we have to note that as we want to maximize the sum, we try to stay on this value as long as possible. Like for example, here in 3 there is no other number, no other value from 1 to n such that the pop count remains 3. So I have decreased it to 2. And coming to 2, it's possible that I can have this number. For example, take this number. Here my pop count still remains 2. Okay. After doing this, I'll go to 1. Here, okay. So our main goal here is to stay on a specific pop count for as long as possible. As long as possible. In this case, it's okay. Now, similarly, if I take some big number, then it will be easier for you to visualize. Like for example, I'll take 2 power 6 where I have 6 set bits. Okay. So initial first step will be decreasing it to 5. And next I can't stay on 5 any longer, so I'll decrease it to 4. For 4, it's possible to stay for one more turn, as I can make this one 1 and simply my pop count will be 4 again. Okay. Now let's go to 3. I'll just write the first few terms, then it will be easier to explain the algorithm. 3. Here I can note that here we can note that we can stay on 3 total. We can stay on 3 for 4 prefixes or 4 turns or something. Here the main observation is that I can't change the immediate 0 here, because if I change the immediate 0 here, it will all those cases have been, all those values have been previously utilized, like having 4 consecutive prefixes as 1, that is our previous case, and all those values are already visited. So I have freedom to change these 2 bits, and maximum possible numbers I can have here is like simply if I have 2 bits, then I can have 2 square minus 1. Like if I have 2 bits, 0 0 0 1 1 0 and 1 1, and also they are lexicograph also they are in sorted order. Okay, so here generalizing the observation, after 3, suppose if I have a 2 here, basically I can't change this bit, and I have 3 bits here. Here I have 3 bits, so I have 2 cube minus 1, that's equal to not 2 square minus 1. I have 2 square numbers, and here 2 cube numbers, because 0 we are also counting 0 here. Here I can have 2 cube numbers, 0 0 from 0 to 8, sorry, from 0 to 7, and we have to simply write the numbers from 0 to 7 in increasing order in their binary representation. Like in this case, what I'll write is I'll start 0 0 1 0 1 0 0 1 1, and the next 3 digits will be same for all of them. 1 0 0, 0 1 1 0 1 1, and the last 3 digits are same. Only the ones that I am changing is the first 3 digits. Okay, so what I am trying to do here is mainly when my pop count is changing, or for example here I'll take this case, when my pop count is changing, I'll check how many zeros I have, how many consecutive zeros I have, and out of them here I have 3 consecutive zeros at start, right? So out of them I can use 2 of them, and have two square numbers after that in those two bits which I can change. Here for example I have these two ones, and these are the 2 square numbers. And here we have to note that the first number at which the pop count changes. Like for example, here initially the pop count is 6 at 2 power 6 minus 1, and the pop count is 5 at 2 power 5 minus 1. Similarly 2 power 4 minus 1 here, and the pop count changes from 4 to 3 at 2 cube minus 1. So basically the pop count changes at 2 power n minus 1, and at every 2 power n minus 1 I'll check how many zeros are before that, and out of those zeros I excluding 1 0 I'll start I'll start filling them with the numbers. Like for example, if I have z zeros before 2 power n minus 1, I have z excluding 1 I'll get z minus 1 zeros, and I'll fill them with 2 power z minus 1 numbers. Those z minus 1 zeros will be filled by 2 power z minus 1 numbers, and that's all. Now let's go to the implementation. So here I am initially what I am doing is I am iterating over all and 2 power n minus 1s here, and From here, I'll initially calculate the number of trailing zeros on 2 power n minus 1. Like for example, 2 power I minus 1 has I bits. I bits as 1. Okay. So remaining we have n minus 1 bits as 0. Okay. So z equal to n minus 1. So I am counting the number of zeros, and remaining bits excluding the 1. For example, I have z zeros and all ones here. Okay. Out of z zeros, I can only use z minus 1 and 1 0. I can't use the 1 0, right? So remaining bits excluding the z minus 1 zeros, I have stored in that remaining n minus z minus 1. Okay. So what I am doing here is I am iterating from j equal to 1 to 2 power z minus 1, because the value 0 has already been included. Initially we are pushing the value 2 per I, right? So while pushing 2 per I, for example, let me take the value of I equal to 3. Okay, I equal to 3 and n equal to 6. Initially I am pushing the value 2 per I. So 2 per I means the case where I have 3 zeros. Okay. Next what I am doing is here I am iterating over all values from j equal to 1 to 2 power z minus 1. Here the value of z equal to 3 and z minus 1 equal to 2. And from 1 to 2 power z minus 1, what I'll get is from 1 to 2 square. Okay, from 1 to 4, I'll simply write the numbers 0, 1, 1, 0, 1, 1. Okay, and I am shifting them by rem. What is the value of rem? The value of rem is simply 4. In this case, n minus z minus 1. What is 6 minus 3 minus 1? That's equal to 4. So after setting the values here, I am right shifting them by 4. Then what I'll get is, I'll get all zeros here, right? And what we have discussed earlier, we want the values to be same there. Like for example, or I'll go to the notepad for better explanation. So initially what we are having, I equal to 3 case, where I have initially pushed this. Okay. So after pushing this, what I am doing is I am iterating from 1 to 2 square, from 1 to 4, and I am filling the numbers here 0, 1, 1, 0, 1, 1. And the value of REM here is 6 minus, here the n equal to 6, 6 minus 3 minus 1, that's equal to 6 minus number of zeros are 3 minus 1, 6 minus 2, that's equal to 4. So I am right shifting the new numbers here by x, and my next step is to take bitwise OR of that with my initial value. What is my initial value here? Here my initial value is simply 2 per I minus 1. And what will happen if I take bitwise OR of 2 per I minus 1? Here we'll simply get all the ones here. As we have after right shift, we are left with only zeros, and if we take bitwise OR, we'll get all the initial values what we have here in the last 4 bits. So here it will happen 1 1 1 1 1 1 and 1 1 1, and that's all. We are done with the construction. So in this way I am pushing the values in the answer array and I am marking them as visited. At last just I am checking that if all the elements are visited or not. If some element is not visited, I will push back in the answer and printing the answer. That's all. Coming to the fifth question. We are given or directly I'll come to the question. We are given a binary string s of length n and an array p of length n and two integers x and y. We have to find if there exist two arrays with non-negative integers of length n such that sum of first array elements will be equal to x and sum of the second array elements will be equal to y. And for every index I from 1 to n, our sum of ai plus bi, ai and bi must be greater than or equal to pi. And another condition is that if the current si equal to 0, then ai must be greater than bi, and if si equal to 1, then bi must be greater than or equal to ai. Okay, here we have almost how many conditions? 1 2 3 4, and we have to find we have to just determine if there exist two arrays such that these four conditions are satisfied simultaneously. So our initial observation in this is that we have summation of ai equal to x and summation of bi equal to y. So if and ai plus bi is greater than or equal to pi. Okay, so if we apply summation of both on both sides here, summation of ai plus bi must be greater than or equal to summation of pi. Okay, so what we get here, summation ai plus summation bi must be greater than or equal to summation of pi. So here the summation of ai is simply the value x summation of ai, and summation of bi is the value y. Okay, so our initial condition is x plus y must be greater than or equal to summation of pi. Okay, initially I'll check for this condition. Okay, so after checking this condition, I'll once go into the edge cases. Like here, if we have si equal to 0, ai is greater than bi, right? And si equal to 1, then bi is greater than ai. So I'll check for the case where I have all values of s are 1. All are 1. Okay. If all the values of s are 1, what I'll get? Then basically what I am getting is at all indices bi is greater than ai. Okay, so suppose we have a1 a2 a3 so on an and b1 b2. bi is greater than ai, which implies that bi is greater than or equal to ai plus 1. So summation of bi is greater than or equal to summation of ai plus n. As we are taking here how n comes is summation of 1 n times. So I am getting n here. So basically y must be greater than or equal to x plus n. So handling the case where all are 1, y must be greater than or equal to x plus n. And handling the case where all are 0, we can do this similarly, and what we'll get here is summation of ai will be greater than or equal to summation of bi plus n, and simply x will be greater than or equal to y plus n. Okay, all 1 and all 0 case. So we have handled the two cases of all 1 and all 0. Now coming to the case where coming to the general case where we have some ones and some zeros. What we have here is our every index sum of ai plus bi must be greater than or equal to pi, right? So considering the case where si equal to 1, here basically pi must be greater than ai. So the value of bi must be at least pi by 2 plus 1. Here we will take the floor division, because if the value of bi is exactly pi by 2, for example, let's take the case where it's even, okay, then all the remaining values will be obviously filled by ai. So here we are getting ai equal to bi. So our bi value must be at least 1 greater than the floor of the p value at that index. Okay. So our condition here is that bi must be greater than or equal to pi by 2 plus 1. Okay. So taking the summation here, like I'll just check the minimum required x and minimum required y. Okay. When si equal to 1, I'll increment minimum required y. I'll denote them by minimum required x as rx and ry. When si equal to 1, I'll increment this by pi by 2 plus 1. When si equal to 0, I'll increment rx with pi by 2 plus 1. Okay. So my next check will be if the value of rx is less than or equal to x and the value of ry must be less than or equal to y. Okay. If both of the conditions satisfy, then only it's possible to have an answer. Else we can simply print no here. Okay. And coming to this case where rx is less than or equal to x and ry is less than or equal to y, I'll simply check the all 1 and all 0 condition. If there are all ones, I'll check for that condition for yes or no. If there are all zeros, I'll check for that condition. Else, my answer will be simply yes. The y remaining will be x. Like for example, here we have rx is less than or equal to x, right? So we are left with remaining x values x minus rx. And remaining y values are y minus ry, right? So here the main intuition is that after as we have at least 0 or 1, we can push all these remaining values into x, or we can push all these remaining values into for example, if 0 I have added pi by 2 plus 1 values from if it is 0, what it means is ai is greater than bi, right? So I have added pi by 2 plus 1 values from x. So I have the option to push my y's either here, or I can also push my remaining y's into 1 as I always have an option. If bi is greater than ai, then if I push the y's into this index, then this inequality will always hold. So intuitively we can see that the remaining values can be adjusted within the array. And coming to the code, simply in this question we have to handle the cases. Like initially I am checking initially accumulate function simply takes the sum of all the elements in the permutation P, and initially if the sum is greater than or equal to x plus y, then my answer is no, as my sum cannot be greater, right? So coming to target I have set the minimum, the pi floor of pi plus 1. I have, at least we have to have this much elements in the x, right? Like what I mean here is, if bi is greater than ai, then at least I have to have pi floor pi by 2 plus 1 times values from array b. Okay. Next, what I am seeing is, if si equal to 0, I am incrementing rx, and if si equal to 1, I am incrementing ri. Okay, checking the case where rx is less than or equal to x and ry is less than or equal to y, else I'll simply print no. Then next I'll check all 0 and all 1 case. If all are 0, then I'll check the condition where x is greater than or equal to y plus n and print s, else I'll print no. If all are 1, then I'll check y is greater than or equal to x plus n. If that is satisfied, I'll print s, else no. And in the case where we have at least 1 0 and at least 1 1, then our answer is yes. Yeah, that's all. Coming to F question. Today's F was a communication problem. Like, I'll summarize the question. Here we are given two players, A and B. Okay. So what A can do is, basically A has the option, we are given two players A and B, and a bipartite graph is given. What A can do is, we are given a bipartite graph, right? So A can color the nodes of this bipartite graph by either of the three colors, R, G or B. R, G, B or so on. For example, he wishes to color this one by G, etc. Okay. And what the main goal of B is to reach the vertex 1, or simply I'll tell what B is given. B will be given an node which is unknown to it. Okay. And what B knows is, it just knows the colors of the adjacent nodes. Okay, colors of adjacent nodes. And the main goal, he also doesn't know the index of the vertex he's on. Okay. So B can only see the color of each neighbor of U, or the U here refers to the or V here refers to the given node. Only B can see the colors of the neighbors of the given node, and what his goal is to choose some J such that he has to move to vertex Uj, and that vertex is closer to vertex 1. That is his main goal. Like, basically, I'll summarize the question in Notepad. Here, what is the work of A? A can just color the vertices with RG or B, RGB color, any one of the three colors. And B will be given queries. Like, for example, B will be given a vertex, and B also doesn't know what vertex is it or the color of the vertex. Only what B knows is that the colors of neighbors of that vertex. Like, for example, if vertex U has three colors, R, G or G or something, B can only know that the neighbors have so and so colors. And what is the main goal of B? B is that he has to select one of these three vertices such that he moves closer to node 1, and these colors will be same or will be exactly the same as the colors that have been colored by A. Okay, so we have to make a strategy such that initially we have to color the nodes with RGB, and while giving uh, while giving the queries for we have to select the vertex such that we move closer to vertex 1. And while writing the code for A, we have to color the vertices with appropriate RGB such that our main goal is to make a combined strategy of coloring and selection such that at every step we moves closer to node 1. Like communication problems are simply like two different problems. Like for example, here if the input contains a string first, we are given number of test cases and 2 n comma m, like the number of nodes and number of edges in the graph, and following with n lives we are given the graph, and we have to return a string. I'll go to the output of the first case. These are the inputs, right? Yeah. For the first case, we have to return a single string s of length n, and we have to denote what colors or the colors of all the vertices in the graph. Okay. In second case, we are simply given an integer dv, number of neighbors of vertex v or degree of vertex v, and after that we are given a string c of length dv, and that string contains the colors of the neighbors of vertex v. Okay, and for second run output, we have to output a single integer j, such that for example, if my node v contains three neighbors u1 u2 u3. Okay, I have to output any value like any index. I have to select one of these three index such that I grow closer to vertex 1, and I have to output the index of that node in the neighbors, and that's all. Okay, coming to the coming to the logic. Here our initial observation is that we are given three different colors and the graph is bipartite. Three colors and the graph is bipartite. Okay, so for example, if this is node 1, bipartite graph means what? We don't have an we can divide the or we call a graph bipartite if there exist two sets such that there are no edges in the nodes containing in the nodes of a specific set. Like for example, in this set, all the nodes here have edges, have their outgoing edges to nodes in another set, nothing within itself. Okay, and that's all. And the important property of bipartite is that bipartite has odd cycle. Bipartite does not contain odd cycle. Does not contain odd cycle. Yeah. So here our initial strategy is to suppose we have a node 1 and immediate neighbors of node 1. I'll color my node 1 with R and immediate neighbors of node 1 with G. and the next neighbors I'll color with a different color. Okay, here I'm simply going making a BFS traversal in my graph. Coming to the next vertex, if I color with the color R, we can see that this vertex has no edge to another vertex such that its color is R. The proof comes from here. As we have odd cycle, uh, as we don't have odd cycle in a bipartite graph, we can say that there are no two there does not exist a edge between two vertices uv such that du equal to dv, because for that to happen the only possible case is that if suppose two vertices are at same depth, then having all the vertices above them, we can see that the length of cycle is odd. So from here our initial observation is that we don't have any edge uv such that du equal to dv. So from every node u, either if we have an edge v, if we have an edge to another vertex v, what we can say is either dv is greater than du or dv is less than du. And our main goal is to, if I am at a vertex u and some vertices v1, v2, v3, so I have to choose a vi such that d of vi is greater than d of vi is less than d of u. Here d of vi means the distance or depth of node vi from node 1 if we make a BFS traversal. Okay, so our main goal is to choose such a word. So coming to our initial coloring, here our main so we don't we are basically coloring giving a same color to every depth modulo 3, and we can note that there is a no edge there is no edge which connects the vertices having same color. Like for example, if I have to connect a vertex edge connecting two R's, only possible case is that they have to lie on same depth, right? Because if I connect any if I have any edge from R to previous R which is a different depth, we can see that it makes a cycle of length 4 or anything like obviously a edge to previous one is not possible, because if such an edge exists, this will be previously colored G itself. Like in BFS, what we'll do is we'll visit all the neighboring vertices of current vertex and color them, right? So an edge to previous R is not possible. So only remaining case is an edge to R in same level. And here we have seen that in a bipartite graph, we don't have an edge such that du equal to dv. So this case is also not possible. So from here I can say that we don't have an edge u comma v such that color of u equal to color of v. Okay. So after making this observation, my next step is to proceed coloring all the vertices as follows. After B, I'll color with R, and next I'll color with next color. For more clarity, I'll take a bipartite graph itself, or we'll take the one which they have given in test 1. Here, what they have is 1 is connected to 6, and 1 is connected to 2, and 2 is connected to 3, 2 is connected to 4, 1, 3, 4, 5, and 7. Here 3 is connected to 2, 4 is also connected to 2 and 6, and also 7, and 5 is connected to 7. So initially what our goal what we are trying to do is, I'll color this vertex by R, and after BFS I'll color in this order, RGB, RGB, so on. I'll color this with red, and immediately 6 is connected to 1, so I'll color it with green. Now I have colored all the vertices at depth 2, and coming to depth 3, I'll color that with B, right? So as 2 is G and 3 is directly connected, I'll color it with B, and 4 also with B, and that's all, I guess. Now coming to depth 4. Okay, 1 second. We are having an edge here from 6 to 5. So 5 also will be colored by B. And coming to and finally we have here, next step is to color the vertices that are directly connected to B. And RGB is done, and again I'll color it with R. Okay. So here our main observation is to note that if I am at a vertex G, I'll try to go to vertex colored R. If I am at a vertex B, I'll try to go to vertex color G. And if I am at a vertex R, I'll try to go to vertex colored B. And we can see that because like if I go to vertex B, I can say that my depth is always decreasing. So I am moving one step closer to vertex 1. So basically our main goal is to check what is the color of our current node, and based on that color I'll see to which neighboring node color I have to move. Okay, but here the catch is that we don't know the color of the node that we are currently in. Like here we can see in the question, only the colors of neighbors of the current vertex we are given, like the color for the current vertex is unknown. Okay, so here our main observation is, if I am at a vertex R and G and B, so, or if I am at a vertex G, consider that I am at a vertex G here, I can see that there is a as we have discussed before, there is no edge such that G is connected to G. So only colors possible for my neighbors are R and B. Okay. So from that we can see that if we are given colors of all our neighbors, the only color which we can simply conclude that the color which is not included in our neighbors is the color of the vertex that we are currently on. Okay, and if we get that color, we can simply see if we are on if our vertex color is G, I'll go to R. If my vertex color is B, I'll go to G, and if my vertex color is R, I'll go to B. Okay, if I get the current vertex color, I'll simply select the neighbor with my with the target color which I want to go or move to. Yeah, that's all. Coming logic part is done, I guess. Now coming to the code. Here initially first handling the communication part. Initially we are given a string s, and if it is first, we have to I am going into solve first function, and if it is second, solve first. Solve first means simply we are given input. Our input is a graph, and we have to output the coloring. And what I am doing here is initializing a BFS and having all possible colors in this color array. Our possible colors are RGB, and I am starting the BFS. And I also have a variable for depth. Here our depth is 0. As we are BFS, after traversing a level, I am incrementing the depth, and we can see that here I am assigning a color equal to depth modulo 3. Like here for depth 0 I am assigning color R, for depth 1 I am assigning color G, and depth 2 I am assigning the color B. Okay, so coming and I am outputting the colors of the nodes. Coming to the solve second, here what we are given is we are given Q queries, and at every query we are given size or degree of vertex V. Okay, after giving after taking that as input, we are given a string S which contains the color of all the neighbors of the vertex V. We are given V, and we are given a string S of size degree of V, and it contains the colors of all the neighbors. Okay, so what I am doing here is I have initialized a map, and what map contains is that the location of current color, like it contain map is char comma int map, and the location of current color in the map. If map dot size is 1, uh, then it doesn't matter to which neighbor I go. Like for example, if my R has all G's only as the neighbor, then I can choose either of them because all of them are equally beneficial to me. Okay, so if all are same, I'll simply output 1. And if map dot size is 2, so map dot size is 2 means I am at a node and I have two different colors here, like color 1 and color 2. What I am doing here is initially I am taking character C as XOR of all the three colors R, G and B, and my next step is to take the XOR of the two colors that are in the map. Like for example, if I have colors G and B in the map, I'll I'll add the XOR of those two numbers. And what happens here is that as I am taking 2 times, the XOR of these two will be cancelled and I'll be left with the remaining character. So here after After getting the color, C is the color of the node that they have given as input. Okay. So if color of the node equal to G, what I'll do is I'll select the node which has color R. If color of node is B, I'll select the node which has color G. And if the color of node is the leftover case is if color of node is R, then I'll select the node with color B. And that's all. Else case is if map.size is greater than 2, and obviously that shouldn't be the case, so I had a assert 0 for safety. Yeah, and that's all. Thank you.